Okay, so good afternoon, ladies and gentlemen, and welcome to the MetaMaterial series of webinars. Today, it's my great pleasure to introduce Professor Jean-François Ganghoffer. He's from the University of Lorraine, Nancy in France. And today, Jean-François will talk about homogenization methods toward the generalized continua and architectured materials.
Thank you, Moamer, for this introduction. So I thank the organizer for inviting me to present a seminar for this webinar series. So indeed, I will speak about recent works dealing with homogenization methods towards generalized continua, and the need for this arises especially if we have metamaterials which are prone to exotic behaviors that we cannot reach with conventional materials. So I will not show you a lot of pictures because you all know a lot of examples of mechanical metamaterials and the kind of responses they can exhibit, like auxetics, which have negative Poisson ratio, or pantographic structures which are prone to strain gradient effects with nearly no Cauchy elasticity. So this work has been based on a few PhD theses. I will first recall the context of generalized continuum theories. So we know that these theories are required to capture effect of rapid fluctuations and with rapid spatial variations at the micro scale. And these continuum formulations, they have the advantage that they introduce some internal material dependent length scales in constitutive law, in contrast to Cauchy theory, which does not include such internal length. And the strain in Cauchy theory is dimensionless, which is not the case, for instance, of strain gradient mechanics. So amongst all these generalized theories which have been developed since early 60s. So at that time, there was nearly no way to produce materials, so to exhibit materials who could correspond to these theories. So it was rather some abstract formulations. And of course, the picture has changed drastically nowadays because of additive manufacturing techniques. So we are able to produce a lot of new microstructures that, for some of them, correspond to these theories. So micromorphic theory is the most general model that incorporates, in fact, a full second-order micro-deformation tensor, which means that each material point, in addition to being able to translate in space, is also able to deform as its own, by its own. And not only due to interaction with neighboring points. And so this micromorphic theory developed in the early 60s by Minlin, Erringen, and followers. Also, there is a nice paper by Paul Germain in the early 70s. It includes actually all higher order and higher grade theories, which can be obtained by degeneration conditions, for instance, by imposing constraints in the micro deformation. So there have been some recent work by Samuel Forrest or Gérard Mogin more than 10 or 15 years ago on the topic. So this is a classification. So this is a kind of genealogy of this generalized continua. I have taken this picture from a work of Samuel Forrest. So we start from field theory. So we have a medium that you describe by continuous theory. And then we have two branches. The first branch on the right, on the left, top left, involves the principle of local action. So we end up with Cauchy continuum in which only the first displacement gradient is of importance. And then we can enrich this Cauchy continuum for so-called non-simple materials by considering two different strategies. So either we include new kinematic variables. So this is called higher order media. So we have Coursera medium, which was developed by the Coursera brothers in the early 20th century. We have micromorphic medium. We have also Coursera medium, and also some other ones I will present later. The second strategy is based on keeping the same degrees of freedom, but adding higher order gradients of these degrees of freedom, like second gradient theory developed by Min-Lin in the middle of the 60s. But most of the time, these gradients are physically relevant for internal variables describing dissipative processes. And the most general theory is, of course, a non-local formulation developed by Ehringen in 72. So this is one classification, and I will come back and propose a new classification at the end of my presentation. So, of course, you know there is still a lot of works going on related to this generalized continua, and because they raise some specific theoretical and also numerical difficulties compared to Cauchy elasticity. So the first one is, if we look at higher order theories, we have new degrees of freedom that emerge at the macro scale that were not present at the micro scale, which, for instance, most of the time obey Cauchy elasticity. Then another question is, what is the a priori ansatz or expression for the kinematic variables to represent in an adequate manner this generalized continua? An important issue is a size dependency of higher order moduli. So if we repeat the unit cell several times, there will be a dependency of this higher order moduli to the number of repetition, which of course is not satisfactory. The question of homogeneity, so some authors in literature find non-zero higher order moduli for homogeneous domains, but maybe the question is, what do we mean by a state of homogeneous deformation? The surface formulation, so you know that Hill-Mendel macrohomogeneity condition was formulated by Rodney Hill a long time ago, more than 50 years ago. It is really at the basis of classical homogenization theory, but also extended homogenization methods when we add new variables or new gradients of the field. And so one issue is still a surface formulation of the higher order static and kinematic variables. So in this talk, we will propose a new version of Hill-Mendel macrohomogeneity condition based on surface, pure surface formulation. And of course, once we have built the theory, it remains to have some suitable numerical schemes to compute efficiently the homogenized higher order properties. So these are the scientific issues I plan to tackle in this talk. I will start smoothly by showing some chiral-Coursera model for this tetrachiral unit cell. So I am moving a few slides forward, and this is the tetrachiral unit cell. So it is prone to rotation, and you know it is prone to tension, to shear couplings, and actually we can use, I'm going to use these couplings at the macro level to balance the weights at the scale of a macro beam architected with such tetrachiral unit cells. But let's start smoothly by showing the classical linear elasticity law relating the small strain linearized tensor epsilon to Cauchy stress sigma. So we have a microstructure, we make some homogenization, and we assume this microstructure obeys Cauchy elasticity as an effective continuum. And if I write it in full, we can see that we have the compliance tensor, which is here, which relates the strain to stress tensors. But usually we do not activate the third column. So the third column includes some coupling moduli between, for instance, tension and shear, which do not show up or very rarely show up for classical solids, for homogeneous bodies. But here I'm going to show that this tetrachiral unit cell, because of its specific topology, will show a coupling between, for instance, tension along X and shear. And so we are going to evaluate the coupling coefficients. So I can rewrite this compliance tensor in the classical form with the inverse of the moduli on the diagonal, and the coupling coefficient chi normalized by the shear moduli. And so for common engineering materials, if we apply a stretch along the midline of the beam, usually we don't get a bending, we get a contraction of the beam due to Poisson effect. But if we have materials with inner shear strain couplings, we may get, in addition to the Poisson effect, by applying a tension, we may get a vertical displacement. And the way to do this is, of course, by using a suitable microstructure. So I'm going to consider architected macro beams. So for the beam statics, I'm using either Euler-Bernoulli or Timoshenko beam at the macro level. If I consider now the full compliance matrix, I need to modify the beam statics to account for this coupling between tension and shear. So this third column, so this S13, S31, S23 coefficients will actually intervene in the beam statics, which will give rise to an enriched model for the axial force, shear force, and the bending moment, as you can see. So here what we did is to compute on one hand by periodic homogenization the coupling coefficient versus some geometrical parameters of the tetrachiral unit cell. So we have angle theta, which is the angle of this inclined beam with respect to the fixed horizontal axis x. And we have also the slenderness ratio, which is the ratio of the thickness of the beam to its length. And then we compare these unit cell predictions with finite element computations done over a fully resolved macro beam with displacement applied on its vertical edge here on the right. And we see a very good agreement between these coefficients. Now we can actually evaluate in closed form the tensile loading, which is either due to a distributed load. So Q is a load per unit length along the span of the beam, or we can apply a vertical shear load at the extremity of the beam. In both cases, we are able to express in closed form the normal reaction. So the goal is to actually apply a normal traction, a pretension that would exactly compensate for the negative bending effects of the weight, the self-weight of this structure. So confident with the validation by finite element, we can use our homogenized prediction for this coupling moduli and then compute the ratio of the vertical to horizontal displacement. So V of x divided by U of x is exactly, after some elementary computation, is exactly the coupling coefficient that you find in the third column in this position of this compliance matrix. And so we want to compare this with experiments. So these experiments were not done in Nancy, they were done at ETH by my colleague Nikos Karanatosopoulos and Dirk Moore. So cantilever beams were micro-architected with this tetrachiral unit cell. You see it's a very small scale. Each unit cell has a size of 20 microns. So it's a very delicate setup, experimental setup. And this micro beam has been fabricated by 2-photon polymerization technique. It is compressed against a flat punch, which is moved at a very low speed of 1 micrometers per second. And then we measure the displacement by post-processing by digital image correlation. So here we measure the coupling coefficient, which has a value of 1.97, which is very close. So the computed one is about 1.95, and of course there is a variance, there is a slope variance in this experiment, which is due to the variance of the slenderness ratio, which accounts for the scatter of experimentally measured values. So now I will move to a chiral Coursera. So the idea is no more to rely on Cauchy elasticity, but to use a Coursera model to account for the effect of rotation. And chirality, chirality is needed. We know from the works of Leitz also that he developed with Benedict, he developed some chiral Coursera model, but it was not based on homogenization. So here we write in 2D the constitutive law. So in this constitutive law, we decompose the stress into a symmetrical part and a skew symmetrical part, but here I'm just writing the symmetrical part of the stress with 4 components, and the second part is actually the bending part relating the in-plane bending moments to the microcurvatures. So I expect to have a fully populated matrix. So I will not explain the classical part of this matrix, just to mention that we have 2 chiral parameters, A1, A2, which quantifies the coupling between the normal stress and the shear strain. We have 2 parameters, B1 and B2, which couple normal stress and rotation gradients. And we have also 2 coefficients, C1 and C2, which couple shear stress and rotation gradients, and they are activated only for non-centrosymmetric microstructures. So from Hill macrohomogeneity condition, which I will not detail here, we can relate the microkinematics to the macrokinematics. So at the base material level, we are using a Cauchy type material described just by the displacement gradient. But we have to elaborate the strain in Coursera theory, as a difference between the displacement gradient and the micro-rotation built as a second-order tensor. So I have Levi-Civita permutation tensor, and phi is a rotation tensor of considering the Coursera rotation. So here you see that I have the symmetrical part of the strain, and I have the skew symmetrical part of it, which is built from the average of the skew symmetrical part of the microscopic gradient of the microscopic displacement. And I am adding here actually the micro rotation effect, which is due to the vector moment of micro displacement with relative position of micropoints. And dual to the kinematics, I can elaborate the macroscopic static variable. So I'm splitting the stress into a symmetrical part and a skew symmetrical part. And the skew symmetrical part is based actually on considering the internal bending moment of Cauchy stress sigma. So then the question is, we have to derive actually in our methodology, we have to split the displacement into a homogeneous part and a periodic fluctuation. Homogeneous part describes the initially heterogeneous medium as if it were exactly identical to the postulated homogenized continuum. And so to derive it, we have a new methodology, which is based on using, in fact, Hill-Mandel lemma and expressing the macro stress, so sigma symmetrical, sigma skew, and the macro bending moment, and then using Hill-Mandel lemma and to get a set of integral relations for the microscopic displacement. So from this, we can reconstruct, in fact, what we call the homogeneous displacement, so the micro to macro kinematics, as you can see here. And of course, this, if we inject it into the work of internal forces, will lead exactly to Hill macrohomogeneity condition for the postulated Coursera medium. So we recover at the macro scale the work of internal stresses with the conjugated kinematic variables. Then, of course, we have to solve for the fluctuation. So we impose the macroscopic kinematic variables on the unit cell, and then we solve these unit cell boundary value problems in a staggered manner. First for Cauchy properties and for Coursera properties. And here we are using, in fact, the decomposition of the displacement with displacement localizators, which means that in turn the microstrain will be related to the macrokinematic variables with strain localization operators. Okay, so at the end of the day, we can compute using Hill macrohomogeneity condition the effective constitutive law, and we have some generic expressions for all this. Actually, we get 6 independent constitutive tensors. This one, C-om, is of course for the Cauchy classical part, and S-om is the one relating the bending moment to the microcurvature. So we can compute all moduli. I will show you one example. The difficulty is to construct the displacement field actually, which correspond to a given mode of deformation. So here we want to apply bending to capture the two moduli gamma 1 and gamma 2. This is a deformed shape of the lattice. This is the set of coefficients with a numerical value, considering these values of the microstructural parameters. So it just gives you an idea. And now I will use this Coursera constitutive law to build and extend the Timoshenko beam model in which those higher order coefficients will enter. So I will have a coupling between normal force and extension, which is classical, and there will be an additional coupling between the normal force and the vertical deflection. And here I can also compute the angular slope of the beam, which will depend on the normal force, on the transverse force, and on the bending moment. So here I am using the homogenized chiral Coursera moduli computed in previous step to feed this enhanced Timoshenko beam model. And I am going to compare, actually, to validate this beam model, we are comparing its analytical prediction with a fully resolved simulation in which we apply a normal tension to this macro beam architected with tetrachiral unit cell. And we observe a very good agreement, actually, between both models. So it means that it is useful to construct such enriched beam model at the macro scale. And second message is that we can build them by doing first homogenization based on the unit cell response. So now I'm extending the purpose of the talk and moving to micromorphic homogenization. So just a few words about the context. So micromorphic theory incorporates actually as I said in the beginning of the talk, a second order micro deformation tensor for each material point in the continuum. It includes all generalized media by suitable generation conditions. There are still some challenges like emergence of new degrees of freedom. If we start with Cauchy mechanics at the microscale, the kinematic representation of the microfields, so micro displacement versus the macro kinematic variables, and also we try to get a scheme in which these higher order moduli are intrinsic to the microstructure, so they do not depend on the number of unit cell repetition. So some pictures. So this is a classical picture about homogenization of periodic media. Epsilon is a small scale parameter. If I make a zoom on this unit cell, we can define the center of area, point X, such that the volume average of the relative microposition will be 0. Whittaker averaging theorem is of special importance. It says that in case of covariant interfaces, so continuous interfaces, the average of the microscopic gradient of a field is equal to the macroscopic gradient of its average. If there is no continuity of traction, there will be some additional jump terms in this relation. So homogenization of periodic media means that we replace this initially heterogeneous continuum by an homogeneous one with effective properties. So let's start by writing the microscopic boundary value problem, which is Cauchy, it obeys Cauchy elasticity. So epsilon is linearized strain, sigma is Cauchy stress, T are tractions, B body forces. So from this, we can write the internal power of forces like this. And now the key idea is to take dyadic products of these micro balance laws with a relative position, so that new degrees of freedom and new balance laws will emerge after averaging. So what we get after a few technical steps is a set of two micromorphic balance laws, which involve, so capital sigma is external stress, capital S is a double stress. You see that it is an average of the dyadic product of Cauchy stress with a relative position. Small s is a relative stress. And these two equations are coupled by the external stress, actually, and capital B and B chi are classical and higher order body forces. And of course, there are some boundary conditions associated with this system of PDEs. From this, we can write the virtual work of internal forces, which can be written in two different ways. Either we use here the classical strain, so the gradient of macro displacement. We use chi, which is a micro deformation and its gradient, or we use the relative strain, and we use also the macro Cauchy stress, which will be dual to capital E. So we get an expression which is a variant of this one, but which basically contains the same information. So the next step is to determine the homogeneous part of the displacement, which links the microkinematics to the macrokinematics of the micromorphic continuum. And for this purpose, we write this set of free integral relations using Hill-Mendel condition. So what we derive actually is the expression of the macro stress tensors versus the micro Cauchy stress. And from this, we are able to reconstruct the homogeneous displacement, which involves the quadratic moments of area tensor, which is quadratic in the relative position. But actually, I should just mention that this is not yet the complete polynomial expansion. So there will be some additional terms up to the fourth order polynomial in Xi. So, but before doing this, we do the converse. So we express the macrokinematic variables versus the micro kinematic ones. So this is done classically by minimizing the squared norm of the difference between the heterogeneous displacement and the postulated homogeneous one. And so we get these macrokinematic variables in terms of the displacement. Then I'm using a new argument which considers the complementary energy density. So complementary energy density is a Legendre-Fenchel transform of internal energy. It satisfies, of course, Euler theorem for homogeneous functions of degree 2. So this relation. And similar to what I did before, I will use these now kinematic relations to determine the polynomial expansion of the stress field. So I will relate the microscopic Cauchy stress to the macro static variables of the micromorphic continuum. So I'm writing a set of integral relations. And after solving these equations for the microstress, I will get this polynomial expression of Cauchy. This is the homogeneous part of Cauchy stress that corresponds to a heterogeneous medium described exactly by the micromorphic effective continuum. So you see it is cubic in the relative position. And now what I can do is to move back from this to the microstrain and to complete the expression of the micro displacement. And by doing this, we get the following quartic expression of the homogeneous displacement. And you see, it was not obvious at all to get it, especially because we have the 6th order moment of inertia tensor, which appears. So it is this part of it is in this P coefficient. And there are some additional coefficients I will not detail here in this presentation. Okay, so now we have computed the homogeneous part of the displacement. We have to compute the fluctuation. The fluctuation is correcting for the difference between the homogeneous displacement and the true displacement of the initially heterogeneous medium. And to compute the displacement fluctuation, we have to solve the unit cell boundary value problems in a staggered manner, considering successively these 3 kinematic measures imposed over the unit cell. So here I'm considering the fluctuation to be periodic. And so it satisfies this minimization of the macroscopic energy density, which is a volume average of the microscopic energy over the unit cell. So based on this, we can compute now all higher order moduli. So we can write formally the micromorphic constitutive law and compute these 6 tensors based on the strain localization operator. So this strain localization operators, they relate the microscopic strain to the macro kinematic variables. And so this micromorphic effective continuum is, of course, useful to reduce the numerical cost of fully resolved computations. So instead, we can feed the computation at the macro level by the computed effective constitutive law. And so I have written just as a matter of convenience, the macroscopic boundary value problem, which is, of course, obtained as the stationarity condition of the macroscopic potential energy over the whole structure. One theoretical aspect is Hill macrohomogeneity condition. So how do we prove in some way a Hill extended lemma? It is just to insert into the microscopic work of internal forces, we insert the homogeneous displacement that we have obtained before. And this allows to identify the expression of the macroscopic static variables versus Cauchy stress. So this is a volumetric version of Hill macrohomogeneity condition. And we can get a surface formulation. So we can use a periodicity condition actually with if we have a unit cell, we can identify two periodicity vectors. So we take a simple geometry of a rectangular box with some microstructure in it. We have two periodicity vectors, and from this we can find actually a surface formulation of all kinematic and static measures that we have derived previously. So now let's move to some numerical results. First, validation of the micromorphic continuum. So what we are going to do is to take a unit cell of a composite, so with a circular fiber. We apply actually sequentially all macroscopic kinematic variables, and we compute the relative contribution of the fluctuation energy to the total energy. So the fluctuation energy is actually the part of the total energy which is stored in the displacement fluctuation U tilde. So it is this volume averaging, and we see that this contribution is less than 1% nearly for all modes. So it means that the micromorphic continuum is a very good approximation of the initially heterogeneous medium. So unit cell size effects. So what we do is to make different unit cell, which includes a repetition of the basic pattern of this pattern. So 1 by 1, 2 by 2, 3 by 3, etc., 10 by 10. Of course, numerical cost is increasing, but this is just a way to check the convergence of this higher order moduli versus unit cell size. And we see that Cauchy moduli do not show any size dependency. And the normalized, actually higher order moduli, they converge very quickly to a steady value, so to a constant value, which is intrinsic to the unit cell microstructure. So this scheme is actually very satisfactory, and the reason for this is that we have incorporated, if you remember, the higher order moment of inertia. So this higher order moment of inertia, they account for long-range interactions between neighboring unit cells. If you just take one unit cell, of course, it's not possible to get a higher order moduli. You need at least to consider 2 by 2 repetition, and this is exactly what it shows. If you compare, we have some fluctuation between a single unit cell and 2 by 2, but after 2 by 2, there is a very good convergence. We reach a plateau. Next, we use this micromorphic model to simulate the response of architected plate here with tetrachiral unit cell submitted to tension. So we compute homogenized properties. We solve the macroscopic boundary value problem by finite element. And we compare the macroscopic response of the fully resolved lattice structure with that of the homogeneous plate. So we first make a macroscopic comparison here. So we see that the slope, the force to displacement slope is nearly the same. So there is a global agreement. And then a more discriminative test is to look if locally the micromorphic medium is able to predict the distribution of the spatial distribution of displacement. And this is the case. So what we plot is a vertical displacement along the center line for the fully resolved network and for the homogenized plate. And we see a very good agreement between them. Okay, so the last part of the talk is about the degeneration of micromorphic to the whole family of generalized continua. So what we are going to do is to map actually this zoom unit cell to back to the physical domain by the scaling parameter epsilon. So what we have done initially is to express the unit cell boundary problem in a normalized, in a zoom unit cell of constant size, so that this boundary problem does not depend anymore on epsilon. But now we are sending this back to the physical domain. And this is why we have epsilon, which appears at different orders in the asymptotic expansion of the displacement. And from this, we can express the strain, and we can express especially the effective moduli using the strain localization operators. We can express the scaling of effective moduli at different orders of epsilon. And you see that they do not scale of the same order. So this is the first message. So Cauchy elasticity will be dominant. And of course, the more we move to enrich behaviors, the more we move to higher order of epsilon parameter. But also another message is that each tensor is itself expanded at different orders of epsilon, except for Cauchy elasticity, which is the dominant term. So rephrase in terms of the constitutive law, this is what we get. So we have, on the left, we have our macro static variables expressed versus the macro kinematic variables, and we have the asymptotic expansion of the homogenized tensors versus epsilon. And so we can see that all higher order tensors of effective moduli split into at least two, if not three, contributions which are ranked in a specific way versus epsilon, and which means that truncated theories can be developed. We could, for instance, neglect power 5 or power 3 terms in this expression here of the relative stress tensor expression. So now the last step is to get actually this family of generalized media by projection of the micromorphic second order tensor. So we are decomposing chi into the hydrostatic part of it, into a symmetrical and deviatoric part, and into a skew symmetrical part. So we have basically three terms here, three different parts of chi. And of course, we can project chi onto either of these subspaces. And by doing this, we get the reduced kinematics and the reduced static macroscopic variables. So I will just illustrate this by considering, for instance, micropolar. So micropolar theory is obtained for micromorphic by restricting chi to be skew symmetrical. And then k will be the gradient of the skew symmetrical part of chi. Microdilatation will be obtained as a theory by taking the hydrostatic part of chi. Microshear will be obtained by considering the deviatoric part of chi. And strain gradient, of course, is obtained by taking chi as a gradient of the macro displacement. And dual to this, we can find the static macroscopic variables, of course, satisfying ill macrohomogeneity condition. So now we get a new tree for this family of generalized continua, which shows three hierarchical levels of degeneration. So we start with micromorphic. By some suitable projection, we can get microstrain, micropolar strain gradient. By a new projection, we get microdilatation, microstretch. And finally, we get microshear and coupled stress media. Okay, so I will show you a comparison, of course, between different effective media, because one critical question still is, if we have a given microstructure, what is the most adequate continuum we should use? Should we use Cauchy? Is it enough to have Cauchy? Should we use the full micromorphic continuum? Or can we content ourselves with, for instance, strain gradient or Coursera elasticity? So to provide some clue to this scientific issue, what I will do is to consider again this tetrachiral unit cell. I will compute its effective micromorphic strain gradient and Coursera moduli, and I will compare the fluctuation energy of these three effective media. So what I can see is that we know already that the micromorphic medium gives a very good description of it. We can see that Coursera gives a poor description for bending. So Coursera fluctuation energy has a very high contribution to the total energy. So if I replace it with strain gradient, I get a much better description. And actually, it's very close to micromorphic, but I can also see that I am not improving predictions of strain gradient continuum by moving to the micromorphic continuum, because the fluctuation energy is actually exactly the same. So for this specific tetrachiral unit cell, we can use a strain gradient continuum. So to conclude, as a summary, we have actually provided some improvement of micromorphic homogenization theories by providing an exact description of the homogeneous displacement as a quartic function of the relative microscopic position. We have brought a constructive proof of ill macrohomogeneity condition. These higher order moduli show size independency because of the higher order geometrical moments which are incorporated into the formulation. We have obtained a whole hierarchy of generalized continua, which are ranked versus a small scale parameter. And we can develop reduced models for architected beams. So of course, there are many perspectives. One of them is to build reduced models, but for architected plates or shells. We have to establish a kind of correspondence between this enriched continua and all microstructures we can actually get from the literature, or many of them, which are prone to such exotic behaviors. And of course, because these architected media are soft, can be fabricated with soft base materials, because they are very porous, they are prone to large strains. So it remains to extend this to a large strain homogenization context in statics and probably also in dynamics. So thanks for your attention. And if you are interested, I have listed a few references that you can find also on the web page of the seminar. Thank you, everybody.
Thank you very much, Jean-François, for the nice talk. So we have time for questions. So people just unmute yourself and feel free to ask any question.